How does orbital mechanics work for Air Force space operations? Imagine a satellite gliding through the vastness of space, its path precisely calculated to accomplish critical missions. The science behind this movement is known as orbital mechanics, a branch of physics that explains how objects move in gravitational fields. For the United States Air Force, understanding and applying these principles is essential for deploying, maintaining, and controlling space assets. Orbital mechanics relies on Newton's laws of motion and the law of universal gravitation. When a satellite is launched into space, it is given an initial velocity and position that place it into a specific orbit around the Earth. The shape of this orbit can be circular, elliptical, or more complex, depending on mission requirements. The key factors influencing the satellite's trajectory include its velocity, the gravitational pull of the Earth, and other perturbing forces such as atmospheric drag and gravitational influences from the Moon and Sun. To achieve and maintain precise orbits, the Air Force employs complex calculations involving Kepler's laws of planetary motion. These laws describe how objects orbit in elliptical paths, with the focus at the Earth's center. The first law states that planets and satellites move in ellipses, with the Earth at one focus. The second law indicates that objects sweep out equal areas in equal times, meaning they move faster when closer to Earth. The third law relates the orbital period to the size of the orbit, allowing engineers to predict how long a satellite will take to complete one revolution. Orbital insertion requires carefully planned propulsion maneuvers. Once a satellite reaches its designated orbit, small thrusters are used to fine-tune its position and velocity. These adjustments, known as station keeping, counteract the effects of gravitational perturbations and atmospheric drag, which can gradually alter the satellite's orbit over time. For example, low Earth orbit satellites experience more atmospheric drag, necessitating more frequent adjustments. In space operations, the ability to predict and modify satellite trajectories is vital for collision avoidance and mission success. The Air Force utilizes sophisticated computer models and real-time tracking data to monitor orbital paths. These models incorporate gravitational influences, solar radiation pressure, and other forces to forecast future positions accurately. When necessary, controlled burns of onboard thrusters are executed to change the satellite's velocity, ensuring it remains on its intended course. Overall, orbital mechanics provides the foundational understanding that allows the Air Force to operate space assets reliably and securely. By mastering these principles, they can deploy satellites for communication, navigation, reconnaissance, and missile warning, all while maintaining the agility to respond to dynamic space environments.